Alright, geometry. Feels like I was just talking to you. I just did all those videos today about the homework from the last day of class, the ones about prisms and cylinders. If you didn't check that out, you might want to do that. I don't know if I want to keep that method where we go over, where I do the homework questions in video. It's still not as interactive as you asked me in class, but at the same time, I'd like you to get going on the next section. If it's a section where the homework doesn't really if you don't get the homework, it's not going to prevent you from doing the next one. I guess that's okay. And that one was kind of one of those. And I guess the rest of the year is kind of like that. Any one section is not really going to help you or prevent you from doing the next one. Anyway, I digress. All right, here's the video questions over the next, what you should be able to do by the end of this video. I'm getting fancy with my 3D graphics here. We got some Perry the Platypi at the bottom of the screen. Yeah, this is about 12.5, which is about similarity. And guess what? Yes, this is the last new section of the year. So this is my last new content delivery section. Oh, you know what? You can't see the bottom of this thing. It's weird. It sort of resizes after a bit here. Anyway, there's the numbers on the Perry stuffed animals there at the bottom. Yeah, so there you go. That's what your question's going to be. These are very numerical in nature. These aren't very philosophical. It's not like I'm asking you sort of what-if questions. I'm actually asking you nitty-gritty, how do you calculate this kind of stuff. All right, so surface area and volume of similar stuff. We did a little bit of surface area ratio, sorry, not really surface area ratio, it was just area ratio, back in the last chapter. It was the last section that everybody hated so much, or freaked out about on the test. In that one, we did some similarity stuff and we did some non-similarity stuff, and there was a difference. When things were similar, you're able to change length ratios into area ratios with this k-squared business, and people actually got that. They were actually accidentally squaring things more than they should have been. So this may be easier because now it's all about similarity. You take k as your length ratio, you square that for area, and guess what? This is the new thing. You cube it for volume. Oh, you know what? I didn't bold this. I can let you watch me bold this live on camera. Okay. So, yeah, fundamental theorem of similarity is sort of a big deal. If the ratio of lengths between two similar figures is k, the ratio of their areas is k squared, and the ratio of their volumes is k cubed. What I mean by that, like the whole crux of the thing, is let's say we have, I don't know, let's say we have a cone. I mean, it could be anything, any three-dimensional figure. We have a cone figure here, and guess what? I'm going to be real fancy. I'm going to make a similar version with the magic of copy-paste. I copy-paste one, and guess what? It's similar. I have a similar version sitting right there. Okay, so whatever these things are, they're similar. In fact, these are very similar because I just made them by copy-paste shrink. I don't know what the radius is, but whatever it is, this one is k times smaller. I don't know what the slant height is, but this one's, k times smaller. I don't know what the height is, but this one's k times smaller. You like the small one first and then the big one? I don't know. Some people like to go from big to small. Some people like to go from small to big. I think of this. I like to think of my k as a number bigger than 1. So let's say this is actually k times h, k times l, k times r, and that the original ratios, or sorry, the original measurements were, sorry, I hope that wasn't confusing. Anyway, say this is the original cone, and then it all got bigger by all that stuff, all the lengths, all the lengths got multiplied, all the one-dimensional stuff got multiplied by this number k. So stuff like height and slant height and radius, stuff like circumference. What else is a one-dimensional measurement? Any 1D thing, all the 1D stuff got scaled up by this factor of k. Diameter would have been a 1D measurement. Slant height, radius, circumference, height. I can't think of any other one-dimensional kind of measurement you'd have on a cone. Alright, so all that stuff is 1D. That just gets multiplied by the same number. And I'll do this with actual numbers next. The surface area of this, I don't know, let's say it was x. X for surface area. The surface area over here isn't going to just be k times x. It's going to be k squared times x. Because if you think about it, this surface area is going to come from some amount of measurements where we're going to have 2 copies of the variables. Like we're going to have pi r squared for the area of the circle, and we're going to have half LP for the or half PL, I guess, in this book for the surface area. When you get two variables are being multiplied there in area stuff, because we have square units, stuff gets multiplied twice. When that happens over here, we get another K times a K. Like we have KR times KL, or KR times KR when we do the squared. The area of the base. So there's going to be a K squared showing up in the difference in the ratio of the surface area. Volume here, let's call it another variable. Let's call it, oh, I don't know. It's going to be some number Q. The volume over here is not just going to be Q or K times Q or K squared times Q. It's actually going to be K cubed times Q. It's going to be K cubed times bigger than the old volume. So it's going to be, because here I'm going to have a pi r squared times h divided by 3. Here I'm going to have a kr times kh divided by 3. Notice I said k 3 times there. So k gets multiplied in 3 times, but when I change from this one to this one. Let me do some actual numbers. And you know what? We could do the same cone. I still have my cone on the clipboard. So let's go paste, paste. Let's do, actually, let's kind of move this around. I like this. I like the idea of the big ones over here. And let's go paste and make that one smaller. I love my perfectly similar stuff. All right, let's say this one has a radius of 6 and a height of, you know what? That's all I need to do. Oh, no, I need more than that, I guess. I need to say something so I have enough to figure out what it is. Let's say this one has a radius of 9. That's going to be slightly messy, but okay. This one's 6. Let's make it kind of a nice triangle. That's going to be 6. Let's say this is 8. That means, well, what would this be? First of all, kind of thing would be like, okay, if that's 6 and that's 9, this is 8, what's that? Well, I like to figure this out and go, okay, what is k? I multiplied everything here by k. 6 times what equals 9? And k is the one-dimensional comparison in the first place. Well, that means k has to be 1.5. I just take 9 divided by 6, I get 1.5. K is 1.5. So I take this 8 times 1.5, I have to get that. The Pythagorean theorem tells me this thing's going to have to be 10. I don't have to do Pythagorean theorem over here. I could, but 10 times 1.5 is going to be 15. Great. Surface area down here, you know what? I could go to the trouble of finding this to figure out this one. In fact, you know what? I will. Just to prove it to you, I'm in that kind of mood tonight. I'm going to go ahead and, yes, prove to you that the surface area is actually in the ratio of, drumroll please, I'm going to make you wait on that. Okay. Surface area down here is lateral area, half PL, plus 1 base, which is a pi r squared, plus B. Actually, I'll say pi r squared. We're sophisticated enough now, we can jump straight to there. Half times the perimeter of the base. Well, the perimeter of the base is 12 pi. The slant height I know is 10 plus pi r squared. Nice. Okay, half times 12 is 6, times 10 is 60, plus 36 is 96 pi. Great. Surface area over here, now here's the whole point of this whole section, is I know this is 96 pi. I don't have to go to the trouble of figuring out the surface area over here. I could just say, hey, guess what, kids? I should just take 96 pi, save myself a whole lot of time, and just multiply that by 1.5 squared, because we're talking about an area comparison. Now, if I really wanted to, I could do half times 18 pi, times 15 plus 9 squared pi, and I'd get, you know what, in the end, I'd get the exact same thing as this. Volume, same sort of thing. Volume over here is 1/3 times the area of the base times the height, which is 12 times 8, which is, oh, you're kidding me? Is it actually 96 pi? Oh, that's funny. 1/3 times 36 is 12. 12 times 8 is, yeah, 96 pi. Now, that doesn't normally happen. And guess what? Over here, the volume is not going to be the same as the surface area, because the volume over here is going to be, I can't believe I made an example where the volume equals the surface area in the first one. But it's going to be, I could go to the trouble of 9 squared pi times 12 times 1/3 and all that stuff. But really, it should just be that. Now, in the end of this section, by the time you really get going, you really don't have to do this stuff anymore at all. They're just going to give you one volume and give you some ratio k, or give you some ratio k squared, and say, okay, how do you convert from this to this? Bang, 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 and go, do you like that? Bang, bang, bang. Here's the area of this one. What's the area of this one? Here's the volume of this one. What's the volume of this one? And you just have to kind of go by, well, I need to get the right exponent on the area ratio or on the volume ratio. Let me actually do those for surface area is 144, 90, whoops, not 144, you moron. It's 1.5 squared. Can't believe I did that. It's 216. This is not 144. It's 216. This is 216 pi. And if I multiply by 1.5 cubed, I need a little more room. The volume is 96 pi times 1.5 cubed, which is... I'm just leaving the pi off because the pi doesn't go anywhere. Pi is just going to be still multiplied by pi. I get 324. It's going to be 324 pi. Okay, great. Now, again, if you wanted to check me on that, sure, go ahead. I dare you. Take 9 squared pi times 12 times a third. I bet you get 324. You know what? I could do that really fast here. 9 squared pi times 12. I said 12 divided by 3. I was feeling lucky, wasn't I? With 324. And the other one would have been a little bit more difficult. It would have been pi r squared on this plus half PL. I'm guessing it's got to be 216. All right. The problems you're going to get are going to be a little more dicey. What if you had... Oh, like I had the pair in the first one. Let me grab something else cool. Okay, I haven't really shared much with you guys about my obsession with Ford Mustangs. All right, so let's say we have a 1966 Shelby GT350 model here that's a certain scale. We have another one that's a different kind of scale. So we have these two model cars, and they're different sizes. But they are similar, and that's the whole point. Let's say we know that the volume of this one... Oh, yeah. Let's say we know the volume of this one is... which could also be something like weight. Weight and volume kind of travel together. They're both a measure of space inside, sort of. So weight is like volume in terms of that. Let's say we know the volume of this thing is, I don't know, 100 cubic centimeters. That might be kind of obvious, or kind of reasonable. So if that one's 100, let's say this one's 50. It's a little bit too nice of a ratio, but just for the sake of example, fine. And I know how much paint it takes to paint this one. Let's say we know it takes enough white paint maybe for to paint this one. And say we know it's exactly, I don't know, 75 square centimeters of paint. The question is, what's the square centimeterage of paint over here? Well, the thing I have to compare, the one channel where I have data on both of these things, is the 100 and the 53. Sorry, the 50 cubes. 100. I know the 100 to the 50. Now you could do this with proportion and adjusting your fractions with cubes and square roots, and we'll do that in class. But the way I like to do it, the way I'm going to show you on video first, is the way most people went. Oh yeah, last chapter when we did the last section about similar figures and ratios and squares and that kind of stuff. We're going to do this and find out that 2 is the value of k cubed. Now, if 2 is the value of the ratio of comparison of volume, that is the cube of the length ratio. To use this, I have to take this this thing and divide it by the... To get from here to here, I have to divide this by the square of the length ratio. Well, I found out that the volume ratio is k cubed, and that's 2. So from that, I can actually figure out what k is. K is then going to be the cube root of 2, which we did in the calculator. You know, I don't know if they're going to get that nasty in the book. This is probably nastier, which is okay. Because then if you can do this, you can do the book ones easy. In the math menu, the fourth thing here is the cube root symbol. Cube root of 2, some gross fraction. It's 1.26, really close. So that tells me that k is 1.26. K squared, then, is actually 1.26 squared, which is weird. It's like, well, let's go back here and not think much about it and go, k squared that for me, please. 1.587. So all I have to do for this number is I have to go 75 divided by k squared, 1.58. Now I'm dividing because I know I want this number to get smaller. This one better be smaller than this one. My k is a number bigger than 1. I always go big over small. That's my little trick. I go big over small, then I always know if I want the number to get smaller, I'll divide. If I want the number to get bigger, I'll multiply. I want to get smaller here, so I'm dividing. 75 divided by that number. Again, I'm just going to leave it in there and go 75 divided by that number. And I get 47.25 is nice. 47 and a quarter. Surprising? It is sort of surprising. I mean, 75 and 100 and 47.25 and 50 are not as far away from each other as they were over here. Anyway, that's fine. These are area and volume. Area and volume. They compare differently. This one compares as a cube ratio. This one compares as a square ratio. I didn't even do anything with lengths. If I did anything with lengths, I would know that all the lengths over here are 1.26 times longer than any of the lengths over here. Like if I knew the diameter of this wheel, divide that by 1.26, I get this. The area of this hood, divide that by 5.87, I get the area of this hood. the volume of the airspace inside, divide that by 2, and get the volume of the airspace inside here. All right, see you in class.